Right. So my first question for you is, when I say they are algorithms without underlying statistical models, what do I mean? Any thoughts or intuition? I'll just, yes.
Like we do not assume some assumptions based on statistics.
Yeah. So yeah, that's a good answer. Can you be a little more specific about what do you mean by assumptions? Mhm.
Like for example, the count method of some
Yeah. So what does that assumption actually mean? Just to go one more step, what does it mean? Why do we need such assumption? Why do we think it's good or not good? Yeah. Hmm. So you mean the Poisson assumption is a heuristic? That's what you mean? Or you mean the algorithms without models are heuristic? Exactly. The algorithms, yeah, thank you for adding to the answer. So what I want to say back to your answer, Hande, is that when we assume, say, the counts follow Poisson, like what we did for that, if you remember several lectures back, that measurement model, right? We have this expression model, measurement model together, they give us one model. For that discussion, what we're trying to assume is kind of like a data generating process. So we're assuming what is the underlying truth that the data come from. So it's always the consideration of statistics, always like there's a signal plus some random noise that gives us our data. So if we have a model, then we can use the signal to help us decide whether our algorithm can recover the signals. But if you don't have a model underlying, you're just doing algorithm, you are doing an operation, a computation on your data, but it's hard to say whether you uncover some truth. So there's no discussion of truth. It's only from data to data. I think that's the key difference. And it really depends on the task, what you're trying to tackle. If you remember in our first lecture, we talked about this inference versus prediction or inference versus learning problem. In that discussion, we say that when we say inference, we want to uncover some ground truth. While when we say learning, it's more on the data. So for example, supervised learning, you're only concerned about whether your predictions of the labels are correct or not, right? So there's not so much discussion about the underlying ground truth. So that's something I just want to elaborate a little more for today. So because the three algorithms, k-means, hierarchical, and the Louvain algorithm in Seurat, they're algorithms, but they don't have underlying model. Yeah, so this is something we have to be clear when we discuss a method. So we're still here, clustering the cells. So last time we talked about the k-means clustering algorithm. Let me try to move this a little bit. So this is the description of an algorithm. It consists of two steps, assignment step and update step. The assignment step is basically assigning every data point to its closest cluster center, also called centroid. And in the update step, we use the new assignment to update the centroid or center as the mean of the data points in that center. So the mean is of the same dimensions as the data points. If your data points are p-dimensional, then your centers are p-dimensional. So it's the mean based on Euclidean distance. So one thing to note that it is kind of, I would say, a disadvantage of using k-means is that you need to specify the k. So, and once you specify k, you need to run the algorithm again. If you want to try different case, then you will run the algorithm for different times. You cannot just run it for once. That's very different from the hierarchical clustering. But the good thing about k-means is that it's designed to give you, spherical-like clusters. So for every cluster, it looks like a sphere. And because you try to minimize the within cluster and distance, right? Basically, these two steps. So one thing we can actually show is that if you define your objective function as the sum of within cluster distance square, if you define it in that way, and within cluster distance can be defined as for every point, I just calculate distance to its closest center, the cluster center it belongs to. then we sum over all data points. So we take the square of the distance and sum over all data points. We can show that each step will decrease the cluster within cluster square distance. That's something we can show. Because it's intuitive that by this assignment step, you would assign every point to a closer cluster center if we update it. So that will minimize that will decrease that term. In the update step, we can also show that within each cluster, this mean is actually the center that gives you the smallest within cluster square distance. And this can be shown just by taking the derivative, right? We take the derivative of the objective against the center. Once we take the derivative, the square will become 2 times the difference. You set that to 0. It's like calculus, and you find the center will be equal to the average. That's how you can show both steps are trying to decrease the objective function. Okay, and this is a cartoon I got from Wiki showing what the iteration means. So it's a very nicely made GIF, which shows that as the iterations go, you will update the cluster assignments, you will update the center. So in this cartoon, the center is marked by this black cross. It's a little bit small, but you will see that it's being updated as you update the cluster assignments. Okay, and it stopped here. But one thing you might notice here already, that is, even though the data points to your eyes may not look like 3 clusters, but if you set k equals to 3, then k-means will for sure give you 3 clusters. And that may not be the thing you want. Okay, so this is the cartoon, and you can also see it on Wiki. So one key question which we started, but we didn't finish, is the initialization problem. As an iterative algorithm, we must set an initialization. And there are 2 natural ways to initialize. The first is to initialize the, initialize the assignment. So what we do is that we basically we first want the forky is to initialize the centers, initialize the k centers. What this forky method does is that it will randomly pick k observations from the data set and use them as initial centers. Then the next step it takes is the assignment. While the random partition method first initializes the assignment, that is, you randomly assign each observation to one of the k labels. Then you calculate the center based on the assignment. Then you update the assignment. So which one is better? Last time we said that for the standard k-means algorithm, the 4D initialization is preferable. And this is from empirical evidence. Specifically, I think k-means plus is an optimized version of, I wouldn't say optimized, that sounds too strong. I would say it's an improved version of the 4D method. So what it tries to do is to find cluster centers as far away from each other as possible. So then you basically want to have the initial centers not crowded in one area of your data space. Then you're more likely to find the right separation partition in the end. So by right, we mean that here on the left, if you put A, D in one cluster, B, C in another cluster, this clustering partition is worse than the right one. A, B in one cluster, C, D in one cluster, because this will give you smaller within cluster variance. So motivated by this, then we hope that if we set the initial cluster center, it will be these 2 bright green ones on the right, instead of these 2 on the left, because you see that these 2 centers are closer to each other than these 2 centers. So the k-means plus aims to find far away cluster centers to initialize, and that will be more like the right one. That's what we mean. Okay, so let's look at the algorithm. What does it say? The intuition behind this approach is that spreading out the k initial cluster centers is a good thing. The first cluster center is chosen uniformly at random, and the data points are being clustered, after which each subsequent cluster center is chosen from the remaining data points with probability proportional to its square distance from the point's closest existing cluster center. So this sentence, second sentence this one is a bit long. What it says is that if you want to choose one data point as a potential next center, you calculate its distance, square distance to the closest existing center, and its probability of chosen is inversely proportional to the distance, right? The smaller the distance, or sorry, not inversely, just proportional to distance. So the smaller the distance, the less likely this point will be picked as the next center. The far away the distance, the more likely we pick. So it's very intuitive algorithm. Exact algorithm as follows. First, choose one center uniformly at random among the data points. Second, for each data point x not chosen yet, compute dx, the distance between x and the nearest center that has already been chosen. Choose one new data point at random as a new center using a weighted probability distribution where a point x is chosen with probability proportional to dx squared. Repeat steps 2 and 3 until k centers have been chosen. Now the initial centers have been chosen. Proceed with standard k-means cluster. So this is the k-means cluster. Okay, so that is introduction of the k-means algorithm, including the initialization. Now let's talk about the number of clusters. One more thing I want to say is that if you run k-means algorithm, it's usually encouraged. I think in the R code implementation, the function called k-means, the default is that it will try 10 initializations. So then from each initialization, it will get a result, right? A partition as cluster, as a set of clusters. Then with 10 initialization, you'll get 10 sets of clusters. Then from the 10 sets, it will pick the one that has the smallest within cluster variance as the output. So therefore, that 10 is a tuning parameter you can tune, you can set whether you have the computational ability to run more initializations, or you want to set a fewer, just depending on your resource. So this also says that even though k-means clustering can be guaranteed to converge to a local minimum for its object function, there's no guarantee of convergence to global optimum. So that's we try different initialization. And this kind of optimization challenge has become more and more universal, more and more widespread in algorithms. Okay, so number of clusters. How do we determine the number of clusters k in k-means clustering? We can base our decision on the within cluster variability or variance. So this is just a rough way to say variability. I wouldn't say variance exactly, because in this definition, here what we're doing is that we call this big CK as the set for data points in cluster K. For every 2 points in the same cluster CK, we calculate their distance, dik, and we sum over the pairs, and then but basically for the pairs, we consider both directions, I to j, j to I. So that's why there are 2 for each pair, 2 distances, the same distance times 2 for each pair. Then we divide by 2 times number of points in cluster K, and then we sum over K from 1 to K. So the reason I don't call this variance because we didn't have the square distance between data point I and the center of CK. So you can have that formulation as well. But here just one type of formulation, just to measure how small the clusters are or how homogeneous the clusters are. So you can see that in this case, if you set k equals n, then every data point would belong to its own cluster. Then just WK will be equal to 0 because every cluster has only one data point. So then we can show that as your cluster number K increases, this WK will for sure decreases because you have more clusters, but each cluster will be smaller. So you will see a decrease. Then just like our choice of the number of principal components, if you remember, we look for the elbow. So we can still apply the elbow idea here. So some people might look at the WK on the log scale. So for the y-axis, you look at log WK instead of WK. So therefore, the value differences wouldn't be so big. That means, okay, if you look at this original scale, and because you are calculating this WK based on the distances, so it's possible that this distance is much bigger than this distance in absolute value. But taking log will preserve their order, but make their differences not so big. So then with the log, you may look at the difference between two adjacent log WK. Like you can take log WK for k equals 1 minus log WK for k equals 2. You calculate the difference, and that's the difference here. And then you can also have log W2 minus log W3 that give you this difference. So here, one idea is that you look for the biggest drop in the log WK difference. In this case, you will pick 3, right? Because from log W2 to log W3, you have a big drop, then 3 seems to be a reasonable case. So this is the graphical method. And there's another approach called silhouette, which is very widely used in evaluating clustering result. So the name silhouette comes from the graph it will give you like this. This is like a silhouette. So if you are unfamiliar with the term, you can check it out. Yeah, basically, I think it's from French. And what it means is kind of like a, how do you say, like a profile, or it's like an image like this. So that's what the shape looks like. So what we do here is that for every data point, say that you already have a set of clustering results, you evaluate the silhouette score, SI, for data point I. What you do is that suppose XI belongs to one cluster A, then you calculate AI as the average distance of the point to other points in cluster A. So it's within cluster average. You also calculate between data point I and every cluster C by calculating the average distance of Xi to other points in cluster C. So this average is over the data points in cluster C. And then out of this many DIC, by many, I mean many possible Cs, you compute the minimum. That is, this is the closest cluster to data point I on average. And you pick this minimum and denote as the BI. So then AI and BI are both distances. AI is just data point I's within cluster distance average, and BI is cluster I's closest between cluster distance. We pick its closest cluster and we calculate the average distance between point I and the points in that cluster. So then silhouette is defined as BI minus AI. We just consider numerator first. What does it mean? If it's a good clustering, then we should expect BI to be bigger than AI, right? The points should be closer to other points in the same cluster rather than other points in another cluster. So BI minus AI should rather be positive. But we want to do a normalization so that the silhouette score is between -1 and +1. By this, we just take the maximum of the two, AI and BI. So you can easily see that we consider the 3 scenarios. What if AI is less than BI? Then the numerator is BI minus AI. Denominator becomes BI. Then you get 1 over AI minus BI. And you can show that this is for sure positive. And it's bounded, upper bounded by 1. It wouldn't be bigger than 1. Similarly, if AI is larger than BI, that's a worst case. In that case, you would have this as BI over AI minus 1. And you can see this is negative. And you can show that this is lower bounded by -1. So silhouette will be between +1 and -1. And you would say data point I has a good clustering result if you have positive silhouette. So if we say k means k equals 2, the silhouette will look like this. So the plot here shows that you are plotting one line, one row for each data point. and you record the cluster of the data point and its closest cluster center, which is taken from this step 3. You find the closest center of the data point and you calculate the silhouette score. So you will see that data point 1 has good silhouette score, and this one has good silhouette score, but this one has not so good silhouette score because it's negative. This is for 2 clusters for k equals 2. And let me see. Yeah, sorry, that's k equals 2. Oh, sorry, this is k equals 3. So I already showed 2 results. So k equals 2, the overall silhouette looks like this. K equals 3 looks like this. So regardless of k, the silhouette plot will always have n rows, right, for n data points. And you look at the overall pattern, or you can calculate the overall silhouette score, just the average across all data points SIs. The bigger the average, the better the clustering result is. So let me ask you, by looking at the 2 plots, k equals 2 and k equals 3, which one would you say is better? K equals 3. Yeah, because just intuitively there are longer bars, right? Yeah, that's what we mean. Yeah, so the overall the bars are longer, meaning that the silhouette is better. Okay, that's the silhouette score. It's also a graphical method. The good thing is that you get one for each data point, you get its own silhouette. So then you can use that for data point specific evaluation. And this is the idea I really like called gap statistic. So this one will actually use this idea of having a reference or negative control for us to decide the number of clusters. Okay, this is from this 2001 statistics paper. It uses the output of any clustering algorithm, such as k-means or hierarchical, comparing the change in within cluster dispersion. So you can call that WK within cluster dispersion or within cluster variability with that expected under an appropriate reference node distribution. So you compare that with some reference value. The main idea is to check whether the observed decrease in WK is significantly better than in the reference control data. The reference data has no clustering pattern, so it's just one homogeneous data cloud. It serves as the negative control for clustering because the K should be 1 for that control. And the reference data has no clustering pattern. But even on that, once you increase the K, the WK will still go down as K increases. So this decrease happens regardless of having a pattern or not, but we use as a reference. So I think this is a very clean idea. So this is what it has. So the gap statistic, so this N means that we have N data points. It's defined as the expectation of log WK under the reference distribution from this one cloud distribution minus log WK. And this is from your actual data, the data you analyze. So the expectation above is with respect to the reference set. The right-hand side quality is the log of the WK we see in our data. We want the gap statistic to be large. So this is the plot. So we have 2 curves. One shows the decrease of this reference expectation of log WK, how it decreases as K increases. So we said it will also decrease. And this solid line shows what happens in our actual data. It also decreases. So we should expect that this reference expectation is always on top of or above the actual data because the actual data should or might contain some clustering pattern. So the WK as within cluster dispersion should be smaller compared to the reference data without clustering pattern. And then the gap statistic will look for the smallest K that has the largest gap. So that's the intuition. So in this case, you will see we'll compute the gap for K equals 1, K equals 2, K equals 3, K equals 4, and pick the gap that's larger. And actually, it's K equals 3. That's what we want. Then the key question is, how do we compute the first term, expectation under the reference? So in the gap statistic paper, it provides 2 approaches. The first one is that given your data, I'm just illustrating the simple case where the data points are two-dimensional. So this is the first dimension, second dimension, and each point here is one data point. So that's what our real data, actual data looks like. And there are obviously two clusters. But how do we generate reference data with only one cluster? So way one is very intuitive. It creates the reference distribution using the range of the observed data. So basically we set a range A to B in the first dimension as the minimum and the maximum of this dimension for all my data points. And the second dimension, I set a minimum to C, maximum to D. So then I have this rectangle, just A to B, C to D. And within the rectangle, I do uniform sampling, sample n data points to create the reference data. This is what the reference data would look like. There's no cluster, seems as if we try to show that, right? We try to show there's no cluster, and the dimension, the range in each dimension perfectly matches that of the real data. But there's a disadvantage. We lose all the other information from data besides the range, right? So if you look at the two plots, you wouldn't say the reference data and the real data look like each other, right? Seem to be so much difference introduced. So then the second approach is more interesting. It uses the principal component analysis we introduced. So specifically, given the real data, say two-dimensional, what we do is that we find the PCs, two PCs, PC1, PC2, as a transformation, linear combinations of the original two dimensions. So now here I call this X prime because I'm projecting my data into this PC space. And I keep the same number of PCs as the number of features. So I don't lose any information. So this is just perfect transformation. This is PC. And then what I do is that I do the same approach in the PC space. I define the ranges of PC1 and PC2, same as the way1. And then I do uniform sampling in the PC space in the rectangle. And finally, I reverse this projection. I go back to my original space and I get a reference data. So you see, the data will look more like the shape of the original data. The reason is because we use PC and the PCs are orthogonal to each other. And so that's why you see in this approach, you may see some correlation between dimensions 1 and 2, kind of positively correlated, but such correlation is lost in the reference data you generate this way. Because here in your generation of the reference data, you are ignoring the correlation between the two dimensions. While in the PC approach, once you do the projection from original space to PC space, you preserve the correlations of the original features, right? And the PCs are uncorrelated. As uncorrelated PCs, it's fine to generate reference data just by preserving the ranges of the PC and ignoring any dependency. And then once we transform it back, the dependence of the original features captured by PC will be restored. That's what happens. Okay, so on the right-hand side, it's showing the linear algebra of what's happening. So basically, this kind of rotation can be obtained using the P by P loading vectors. Let me just get it this way, right? Because for every PC, it has a P-dimensional loading vector. P is the original feature number, but now we want P PCs, so we don't lose any information. Okay, so I think even if the linear algebra might be new, but I hope this cartoon illustration will make sense to you. Then this is the gap statistic algorithm. Let me quickly go over what it says. So first, we cluster the observed data x1 to xn. We vary the number of clusters k from 1 to some maximum we set. That means that's the maximum number of clusters we want to tolerate. And for each k, we calculate the WK as the within cluster dispersion. That's for the actual data. Then reference data. We generate capital B reference data sets from the first way or the second way. I will say the second way is preferred, and cluster each reference data set under each k. So we obtain WKB star. So K still varies from 1 to the maximum. B is just indicating the index of the reference data from 1 to capital B. Okay, and then we compute the gap statistic just as the average of those log WKB star across B. It's the average across B for each K minus the log WK, which is the same K from the observed actual data. So we do this for each K. Okay, so it seems that from here, we will just look for the K such that the gap is the largest. But we also, because this is a paper by statisticians, they consider the standard deviation. They consider the standard deviation across the log WKB stars across the B references, right? Because we generate a reference data for B times, so we want to evaluate their standard deviation. And that's this SDK. So for each K, we have the standard deviation across the capital B reference data sets that give us some uncertainty. Ultimately, we pick the K in a conservative way. That is, let me see, I think I missed that figure. Sorry, my bad. Well, I should have it. So what we do is that we choose the K as the one if it's larger than the next gap at K plus 1 minus standard deviation. So it's just like we compare the gap K to the next one's lower bound. If it's bigger than the lower bound, we stay at the current K instead of moving forward. So which means that we have preference to choose a smaller K, right? And we're comparing the K, we're not comparing gap K to gap K plus 1. We are instead comparing gap K to gap K plus 1 minus standard deviation at gap K plus 1. So that makes it more likely that we choose K instead of K plus 1. Okay, so that's being conservative. Okay, that's what I want to say about gap statistic. So please note that this idea applies not only to k-means, but it can be generalized to any algorithm, any clustering algorithm, if you want to compare different cluster number with some reference. So the idea is general. Okay, hierarchical clustering, which is called agglomerative clustering, which means that here in this cartoon, every species is one data point. You try to aggregate them gradually into one cluster. So here, in this case, the aggregation has some natural meanings. Right? On this layer, you're aggregating them to like birds, mammals, more than 3 legs, and then further, these two can be aggregated to vertebrates, and then finally, they are called animals. So it's just like you have this tree, hierarchical tree, which k-means cannot give you, right? K-means by design doesn't give you this nested structure. That means if you have k and k plus 1, it doesn't mean that the k plus 1 clusters can be combined into your k clusters. There's no such guarantee for k-means. So for hierarchical clustering, the steps are as follows. One thing to note is that if you have n data points, you will first compute a distance matrix. So you get an n by n distance matrix. But this is something interesting. That is, even if you don't have your original data points, you just have an n by n distance matrix, you can still do hierarchical clustering. So your input may be a data matrix or a distance matrix. But for k-means, you must start with data matrix. There's no way that you can do it using distance matrix. And so I can share with you that there was one observation of a bioinformatics method paper, which I found to be striking. That is, the input is an n by n distance matrix, but that method uses k-means. So in that case, it's not reasonable because it's treating this n by n distance matrix as if it is a n by p data matrix. So then when you are doing the k-means, what you are doing is that you're grouping the n rows based on their distances to themselves, right? So it's kind of weird. But you know, the funny thing is that if you run k-means code, the function on this matrix, you will get result. But logically, I wouldn't say it makes sense. So that's another thing I want to draw your attention to. So sometimes we have to understand what's going on to use the function correctly. Like there's no error report doesn't mean it's correct. But I think the error report is just the easiest check. Anyway, so you compute the distance matrix, and then you, in this step, you will merge the closest data points into clusters. And then you will update your matrix, distance matrix from data point to data point matrix to become some of the data points will now be clusters. So you merge data points to clusters, and each cluster will be your new data point. And then you do the merging again. So it's like iterative until you have just one cluster. So let's take a look on what happens. So as the hierarchical clustering, once after step one, some of your data points will be replaced by a cluster. And that's, as I said, the cluster is your new data point. But then it means that we need to define a distance metric between clusters. So this includes the distance between a point and a cluster because we can see every point as its own cluster. So this is the key step. So in hierarchical clustering, besides the need for a input distance matrix, you also need to specify how you define the cluster to cluster distance. And there are three commonly used linkage. They call linkage, but it's just a way to link two clusters. So just to start from the beginning, here we don't have to specify K because you will get this whole hierarchy tree. It's also called a dendrogram. A dendrogram will be built. It is an agglomerative clustering, and we will need two things. First, distance metric required for every clustering method. Second, distance between a point and a cluster and between two clusters. Some choices are single linkage, which means that between two clusters A and C, you pick the smallest distance between a point A and a point in C. So for each cluster, you pick one point, compute the distance, and you pick the smallest distance to represent the distance between the two clusters. On the opposite side, complete linkage picks the maximum distance among all pairs. Average linkage just take the average of all pairs. And this is the cartoon. So this is a single linkage between clusters A and C. You pick these 2 points because they're closest. Complete linkage will pick these 2 points because they are farthest away. Average linkage just computes the pairwise distances between points and take the average. Okay, so as I just said, hierarchical clustering has the distinct advantage that any valid measure of distance can be used. In fact, the observations themselves are not required. All that is used is a matrix of distances. That's input. And here, another note, the choice of metric as well as linkage can have a major impact on the result of the clustering. Where the lower level metric determines, the lower level means the distance metric determines which objects are most similar. Whereas the linkage, the 3 linkage criteria influences the shape of the clusters. For example, complete linkage tends to produce more spherical clusters than single linkage. What is the intuition here? Because for complete linkage, it's harder to combine, right? You will combine these two only if this maximum distance is small enough, which means that if the maximum distance is small enough, then all these other pairwise distances must be even smaller. So then all the points are close to each other after the merging. While for single linkage, you're only looking for the smallest distance, which means that even though the smallest distance is small, but other pairwise distances can be big. Therefore, after the merging, the cluster may be kind of diverse. That's the difference. Okay. So I'm going to show you one example about how we can do hierarchical clustering by hand if our n is small. So here we have just 5 data points. And in the input, we calculate the pairwise Euclidean distances among them. So between x1, x2, distance is 1. Between x2, x3, distance is 4. Between x3, x4, distance is 2. And then we have 5, 5.5, 6, 7 for other distances. So given that input, how can we do the hierarchical clustering using single linkage? So first, among all the pairs, we pick the pair that have that has the smallest distance. And it should be between x1 and x2. Distance is 1. So we merge them. And in the dendrogram, what the y-axis, it marks the distance at which the merging happens. So here I'm just showing that x1, x2 are merged at a distance of 1. So because their distance is 1. Then you see I will treat x1, x2 as one cluster, one data point for now. So let me try to, so after the merging, they become one cluster themselves. So I consider them to be 1 point. And then I evaluate this point versus x3, x4, x5. And I use single linkage to define the distances. As single linkage, you see, between this cluster and x3, it's 4. The distance is 4 because I picked the smallest distance. Between this and x5, it's 5, where I'm choosing between 5 and 5.5. 5 is smaller. Between this and 4, even though I don't write it down, but it seems that this distance is bigger than between this and x3. So therefore, the next smallest distance among these 4 points, cluster x3, x4, x5 is 4. So then, my bad, it's not 4. It's between x3 and x4, right? These two have a distance of 2, and that's smaller. So that's why the next merging happens here. I combine x3 and x4 at a distance of 2. So they become one cluster and one new data point themselves. Finally, I have just three data points, here, here, and x5. And I use single linkage to define their distances. So between these two, 4. Between this one, x5, 5. Between this one, x5, 6. So 4 is smaller. Then my next merge is between this and merge them at 4. So then you see, I would call them one cluster. Okay. Then finally, it's combining this cluster and x5. And that distance by single linkage is 5. So that's why the last combination happens at distance 5. And that's all. So this is the agglomerative clustering. We do that step by step. Okay, and then there's some running time discussion between k-means and hierarchical clustering. Because for k-means, we're using this heuristic algorithm called Lloyd algorithm. And then it's actually, it can be considered as a linear in n. It's n times k, number of clusters, times d. D is the number of feature dimensions. We called p before. I is the number of iterations until convergence. Please note that when you run k-means, you always have a maximum set on I. You wouldn't let the algorithm run indefinitely if it doesn't converge. Because convergence means that there's no more update on the assignment. And we always have an upper bound on that. So with this upper bound, the time is actually linear in k, linear in n, which is good. But for hierarchical agglomerative clustering, it has actually this order of n cubic, which is actually quite slow if you have the data set, the n size to be large. However, there are some efficient methods being proposed, which reduces complexity to n squared, which is something we use in practice. Okay, and just for your information, in R, when you run a heat map function, the heat map.to function, then by default, you will get a hierarchical clustering done on your rows and columns. The dendrograms will be automatically output. So one more method I want to introduce on top of k-means, it's called tight clustering, which I think is a very interesting idea. So the idea is that we don't want to necessarily assign every data point to a cluster. We can leave out some data points unassigned. And then we want the resulting k clusters to be as tight as possible. So we hope to find tight clusters at the price that some data points may not be assigned. That's the idea. And it may be useful in some cases where you just want to find some modules, for example, modules in your data, but you don't care that some data points don't belong to any modules. Maybe if sometimes you want to cluster genes, that may make sense instead of cells. So it really depends on the context. And what the algorithm did is based on subsampling and repetition to find stable clusters. That's the idea. Say you sample a proportion of your data points for example, 70%, you can change to 80%, 90%. But this is just a proportion. You want to try to add some, uncertainty to your data so that every time you sample 70%, they won't be exactly like each other. But you can imagine that if we reduce this proportion to a smaller percentage, then the subsamples will be more different. While on the other case, if you subsample 100%, then it's the same data again and again. So I should say sample without replacement. Then on the subsample, you apply the k-means to get k-cluster centers. And given the centers, you assign the rest of the data, 30%, to the k-clusters by closest Euclidean distance. And you repeat this for capital B times. Then, this is the key. You will construct co-membership matrix C. So Cij, so this is actually a wrong notation. It should be at 0 to 1, I should say, this is actually n by n dimension. You get this matrix C, n by n. N by n means that it's the n data points co-membership matrix, where Cij is the proportion out of the B subsamples and clusterings that points I and J belong to the same cluster. So I don't care what the label they have in each subsample clustering, because it's possible that I and J were both assigned to cluster 1 when we do this for the first time, and they're both assigned to cluster 5 in the second time. That doesn't matter. I only care whether they are in one cluster, because the cluster labels are not the focus. So here, this co-membership proportion is just saying, if I capital B 100 times, then out of 100 times, how many times I and J are together? That's the proportion. That means how stable their co-membership is. Finally, I want to partition my n data points based on C. That is, I set a threshold alpha, say alpha equals 0.5. I want to find clusters such that in each cluster, all the pairwise co-membership proportions are bigger than this threshold. Sorry, I should say if alpha is 0.1, then I'm looking for 1 minus alpha, that's 0.9. So I'm looking for the data points that they are co-member with each other for at least 90% of the times. So this is how I will get high clusters, right? So basically, but once I change the threshold, I will find more or fewer clusters depending on the threshold. But essentially, the smaller the alpha, the bigger the 1 minus alpha, the tighter the clusters are. Okay, then my question for you, since I already introduced k-means clustering, which is used in step 1, what can I do to achieve step 3? So you have a co-membership matrix, and all the entries here are between 0 and 1. What do I do to satisfy what I need for step 3? That is, how can I find the clusters if my target co-membership is at least 1 minus alpha? Any idea? Right, this is the key step, right? Otherwise, even though I give you the C, there's no way for us to get to the clusters. Okay, the hint is what we just covered. What algorithm we just said can take the input just as a distance matrix? The hierarchical clustering, right? So we can convert, you can see this co-membership matrix as a similarity matrix, and we can do 1 minus C as the distance matrix. And then basically alpha is the distance, while 1 minus alpha is the similarity. So then we can just say, okay, given 1 minus C as the distance matrix, we do hierarchical clustering, and for the threshold, distance threshold alpha, we want basically each cluster to have within cluster distances all below alpha. To achieve that, we do complete linkage. Because for complete linkage, once you do the combination, you make sure that all the within cluster distances are under that threshold. That's what we want. So we do hierarchical clustering using complete linkage. That's how we can achieve step 3. Okay, so you can see that hierarchical clustering is very useful. Besides a clustering algorithm itself, it can also be used for other purposes. If you want to find very tight clusters so that each within cluster distance is bounded by something, you should do hierarchical clustering with complete linkage. Okay, so finally, let's move to Seurat. This is an interesting question I want you to think about. K-means and hierarchical clustering are classical, useful, successful algorithms in practice. However, for single cell clustering, it ended up that Seurat doesn't use them. Seurat uses graph-based clustering. And I think this is a big open question for computational people to think, why is it better? Yeah, people might have seen empirically better, but why it's principally better, right? Why does it make sense to first convert our data into a graph and then work on the graph? So let me first introduce graph-based clustering first, and I hope you can bear this question in mind. And I can be honest with you that I don't have a very good answer. I don't have a solid answer. Yeah, but I think it's something very interesting. Like, when do we want to convert our data to a graph when we don't want to do that? Because graph here is like an intermediate step. It's not our final target. But empirically, people found this to be a very good approach. And I can also see that this is a very big difference between algorithm builders and statistical modelers. I think for algorithm builders, they're not afraid of trying different algorithms and test which one empirically gives the best result. But for statistical modelers, they want to start with something they understand, right? The good thing is that then the algorithm you come up with might be more principled. But the downside of it is that you are basically limited of what you can try. So there's a pro and con for both. Anyway, graph-based clustering. Seurat applies a graph-based clustering approach, building upon initial strategies. In this paper, importantly, the distance metric, which drives the clustering analysis based on previously defined PCs. Don't forget that in Seurat, we have done PCA. So now we have cells in the PC space. So the data matrix now we work on is a cell by PC matrix. The PC is from the PCA step, and that number of PCs is our choice. In this example, in the tutorial, the Seurat author just chose 10 PCs. So now we have 10 dimensions. Remains the same. However, our approach to partitioning the cellular distance matrix into clusters has dramatically improved. Our approach was heavily inspired by recent manuscripts which apply graph-based clustering approaches to single-cell RNA-seq data, including this SNN-click and CyTOF data phenol graph. Briefly, these methods embed cells in a graph structure, for example, a k-nearest neighbor, shown as KNN graph, with edges drawn between cells with similar feature expression patterns. And here the features are PCs. And then attempt to partition this graph into highly interconnected quasi-cliques or communities. We'll give you one figure. As in phenol graph, we first construct a KNN graph based on the Euclidean distance in PCA space. Yeah, PCA Euclidean distance between two cells in the PCA space, and refine the edge weights between any two cells based on shared overlap in their neighborhoods, local neighborhoods, called Jack-Hurd dissimilarity, which we'll introduce. This step is performed using find neighbors function in Seurat and takes as input the previous defined dimensionality of the data set, first 10 PCs. Okay, so this is the KNN graph for K equals 5. So I found this online, and what it says is that basically here your data points are just two-dimensional. So I'm presenting the whole data. So what it means is that you connect every point to the 5 nearest neighbors. So this data point is connected to
this one, this one, this one, this one, this one. So from every point, you have 5 edges to the 5 nearest neighbors. From this point, I have this one, this one, this one, this one, this one. So you see that that's the 5 neighbors I consider for this data point. So for every data point, I connect it to the 5 nearest neighbors. Okay. But here you want to see that here, this connection is actually directional because from this point, I have its K and N. From this point, I have its K and N, but it's directional. It's not bidirectional, right? That's the key thing to remember. So then this graph, K and N graph, will be refined as shared nearest neighbor graph called SNN graph in SRAM. So for SNN graph, what you're calculating is that between every 2 points, you calculate the so-called Jaccard index, which is defined as the size of the intersect of 2 sets, intersection size over the union size. I take the intersection of 2 sets, calculate the size. I take the union of 2 sets, calculate the size, and intersection size over union size, which is bounded between 0 and 1, right? That's the Jaccard index. If the 2 sets are just identical, the Jaccard index is 1. If the 2 sets have no overlap, no intersection, it's 0. So therefore, for Jaccard index, what we mean here is that, for example, for this data point, I take the 5 nearest neighbor as a set. And for the other points, I take its own KNN set. And then for the 2 sets, each set has 5 nodes. I do the Jaccard. And then this Jaccard index will give me this edge weight between this point and this point. Okay, so this point has its own KNN. This point has its own KNN. Then if they're identical, both the numerator and denominator will be equal to K, right? K, the same K neighbors, then Jaccard is 1, so the weight is 1. Otherwise, if there's no overlap between them, it's like this point and this point, their KNN has no overlap at all, then this is 0. So then I don't have an edge between them. Okay, this is what we mean by shared neighbor graph. That's the data transformation. So from now on, we no longer work with our data matrix in SRAM, but we work with this graph. Okay, this is the find neighbors function in SRAM. And there are 3 parameters we need to pay attention to. K. How do you define the K in the KNN? In SRAM, default is 20. For every cell, you find the nearest 20 cells in the PC space. And also, the default is to compute SNN. Because you see, in the argument, compute SNN is the reverse of return neighbors. And return neighbors default is false. So then compute SNN's default is true. Then you will construct an SNN graph, shared nearest neighbor graph. And then that means you will compute that Jaccard index. And with the Jaccard index computed for every 2 cells, there is another key parameter called prune SNN, which by default is set to 1/15. What it does is that it sets the cutoff for acceptable Jaccard index when computing the neighborhood overlap for the SNN construction. That is, any edges with values Jaccard index less than or equal to this 1/15 will be set to 0 and removed from the SNN graph. Essentially, if you set this to 0, then there will be no pruning. All the edges, all the Jaccard indices will be kept. If it's set to 1, then you prune everything. There's no more edges. So you see that these 2 parameters, K parameters, K and the prune threshold, will determine what the graph looks like. And these are the default values. And I have to just say that for most people, maybe they never tune these 2 parameters. But essentially, again, they were chosen maybe, I think, by abundant empirical trials. But I think theoretical understanding is far from here. Okay, to cluster cells. Okay, then given the graph, right? Given the graph like this, how do you partition them into communities? Maybe I can ask your opinion for here. How would you partition them into communities if I gave you such a graph? By community, The definition is that I want the edges to be dense within each community, and I want the edges to be sparse between communities. What's your intuition given such a graph? And the reason I ask this question is because for unsupervised learning, like clustering, there's no ground truth, right? So it's always about what's your criterion, what is your intuition, what would you see as reasonable? And also I can share with you that this graph is just randomly generated. So that data has no real structure. So you can have something like this. So yeah, so basically graph-based clustering will try to partition the nodes into communities. Hopefully within communities, the edges are dense. Between communities, the edges are sparse. That's just the thing. Okay, so probably I would say like I can possibly divide them into two communities by cutting here. That's what I guess. But anyway, yeah, so that's what Sierra does. They apply this modularity optimization technique, such as the Louvain algorithm, which is in this paper. Louvain is in this paper, which I will introduce. Louvain is the default in Sierra to iteratively group cells together with the goal of optimizing the standard modularity function. And we'll introduce what is modularity, which is a term used in networks. The find clusters function implements this procedure and contains a resolution parameter. This is a key parameter that will determine how many clusters you will get. But it's not as straightforward as the K in K-means. Like there's almost no like one-to-one translation between resolution and the K. It depends on the data set. That sets the granularity of the downstream clustering. With increased values, leading to a greater number of clusters. So the larger the resolution, the more clusters you will get. We find that setting this parameter between 0.4 and 1.2 typically returns good result for single cell data sets around 3,000 cells. Optimal resolution often increases for larger data sets. The clusters can be found using the idents function to give you the cluster membership of each cell. But I want to say that in practice, many people may just do this trial and error thing, right? They try the resolution and see it. But how objective that is, that's another question. Okay, so Louvain. This is the Louvain paper. It's very interesting that this is an archive paper, a preprint paper by people, I think, in like mathematics, computer science. That has become very popular. What's the reason? If we read the abstract, we will get why. So it's called fast unfolding of communities in large networks. We propose a simple method to extract the community structure of large networks. Our method is heuristic. It's a heuristic method that is based on modularity optimization. It is shown to outperform all other known community detection methods in terms of computation time. Moreover, the quality of the communities detected is very good, as measured by the so-called modularity. This is shown first by identifying language communities in a Belgian mobile phone network of 2.6 million customers, and by analyzing a web graph of 118 million nodes and more than 1 billion links. The accuracy of algorithm is also verified on ad hoc modular networks. So the biggest advantage is fast. Yeah, that's why it's very popular, because single cell data can also be fast, can also be large. And the name Louvain comes from the author's affiliation. They are in Louvain, Belgium. That's the reason. It's the location. Okay, the Louvain clustering, the problem is for this community detection problem, which is a specific term for clustering used for networks. Okay, or graph-based clustering. But it's basically every community is a cluster. Requires the partition of a network into communities of densely connected nodes, with the nodes belonging to different communities being only sparsely connected. I think the reason why clusters are called communities in the networks because of social network, right? When you divide people into clusters, they have this interpretation as communities. Precise formulations of this optimization problem are known to be computationally intractable, unfortunately. So several algorithms have therefore been proposed to find reasonably good good partitions in a reasonably fast way. The quality of the partition resulting from these methods is often measured by the so-called modularity of the partition. So this is a very important concept to understand. What is modularity? It is a scalar value defined for a partition. A partition refers to a set of clusters. Its value is between -1 and +1. It measures the density of links inside communities as opposed to links between communities. So we only have the links between, actually, we only have the links, let me see. We only have the, I wouldn't say we only have the links between them, but this is basically in the indicator. Let me just try to go to the formula next. The indicator indicates that, okay, Ci and Cj are the communities of I and J. They have to be equal. So then I count this term because this delta function is binary. It's a binary indicator. When Ci and Cj are equal, delta function is 1. Otherwise, it's 0. If it's 0, I'm not counting this term in the summation. Okay, so even though I enumerate all points I and J in the sum, but only when Ci and Cj are equal, I and J in the same community, I count this pair. That's it. So in cases weighted networks are networks that have weights on their links. That's what we have for the shared nearest neighbor network, because the weights are Jacob indices. So these are between 0 and 1. So this is a modularity. So in the sum over data points I and J, every 2 data points I and J, Aij represents the weight of the edge, like the Jacob index. Ki is the summation of the edges of I. Kj is the summation of edges of J. So this term, Ki times Kj divided by 2m. M is the number, sum of all the edges divided by 2. So you can basically have 2m. 2m can be more easily interpreted just as the sum of all edges. So Ki times Kj divided by the sum. We take Aij minus this thing. So it's basically roughly intuitive, I would say. This is measuring like, okay, the weight between I and J, how different it is between like assuming I and J are randomly connected because of just by chance. So basically, this is like an expectation out of randomness, and we take the difference, we take the sum. That's the modularity. Yeah, probably we should stop here since we are running out of time. And on Wednesday, we will have our special reader, Zhiqian, to give a tutorial on the cell type annotation, which you will do for your final project. And then we'll resume our lecture on next Monday.